Okay, now we're going to talk about the memory table space. The memory table space stores data that resides in memory. Therefore, it is used for high performance of data processing. So when we create memory tables, they are saved into memory table space, which is located in memory. This memory area, where memory table space is stored, has the property name called memmax DB size. Okay? The default value is 2 gigabytes. The memory data resides in memory only. Therefore, it is volatile. So you guys would think there could be data loss whenever there's a system shutdown. However, Altibase HDB provides a backup file for the recovery. They are called checkpoint image files. For a single memory table space, two checkpoint image files are created. Also, the redo log files are used for the recovery as well. So whenever the checkpoint is executed, the information for memory table space is backed up to the checkpoint image files located in a disk. And whenever the DML, such as insert, update, delete statements are executed, that information is stored into the redo log file, which is located in the disk as well. So both checkpoint image file and redo log file stored in a disk are used for the backup and recovery for the memory data. The checkpoint can be executed by time interval and by the number of assigned log files are created. Firstly, for the time interval, the checkpoint can be executed every 1 hour, 2 hours, or 5 hours, or etc. Secondly, the checkpoint is executed by the assigned number of redo log files are created. So, for example, when every 100 or 500 log files are created, the checkpoint is executed. So when checkpoint is executed, the modified data from the memory, so-called dirty page, is backed up to the disk area. There are two checkpoints, and they are called fuzzy checkpoint and ping pong checkpoint. When checkpoint is executed, both of them are executed at the same time. The term fuzzy refers to the fact that performance of transaction is not affected during checkpoint, and ping pong refers to the fact that checkpoint writes the memory data in two sets of files, checkpoint image 0-0 and checkpoint image 1-0, something like that. Okay, so it writes the memory data in first file and the second file, and it goes back to the first file and so on. Okay, now I'm gonna talk about the allocation of space and the page status. The reason why we need to study about page status is because the allocation of space and the page status are related to each other. Meaning, whether the page can be reused or not is depending on the page status and the space allocation. Okay, so I'll be talking about the types of page status and how they are changed and how they can be reused once they are changed. Okay, so they are classified by either free or used. The space allocation of memory table space is 32 kilobytes page units. Okay, the page status could be different when a page is in a table space or when a page is in a table. So when a page status is free in table space, it means it is not allocated to any table yet. Therefore, it is ready to be allocated to any table. But when page status is used in table space, it means the space has been allocated to a particular table. Therefore, the page cannot be reused by any other table until the table returns the page to the table space. Okay, let's look at the table. Likewise, when page status is free in a table, the space has been occupied, but it contains no data. And that page can be reused only within the table. Okay, when page status is used in table, it means the space is allocated to a table and it contains some data. And because of that page can be reused until the data is deleted. Okay, so whether the page can be reused or not is determined by the page status, because the page status changes every time the space is allocated or when space is deleted, or when the space is returned to the table space. Okay, so now I'm going to talk about how page status could be changed, especially when delete, truncate, and move are executed, and also how they can be reused or not. Okay, first of all, the delete statement. Okay, when delete statement is executed, the page status is changed from used to free, but that free page is reusable only within the table. Okay, that is because when delete statement is executed, the free page is not returned to the table space. So even though the free pages are deleted, the other tables cannot use them as they are not returned to the table space. However, there is something called compaction. Okay? When compaction is performed, the free page is returned to the table space so that the free page can be reused by other table. Okay? The compaction is only allowed in memory table space and volatile table space. Okay, also, when truncate statement is executed, it deletes the data just like delete statement, and the page status is also changed from used to free. However, like delete statement, the truncate returns all the free pages to the table space, so other tables can use that free pages by being allocated from the table space. Okay, the move statement. A lot of you may not be familiar with move statement. Okay, the move statement is also DML that inserts record into target table and deletes record from the source table. Okay, and this function has the same effect as delete, meaning the page is not returned to the table space, so that page can only be reused within the table. Okay. However, when compaction is executed, the page is returned to the table space. Okay, so the delete and move statement do not return all the free pages, but whereas truncate statement returns all the free pages once they are executed. Right? Okay, so now we're gonna have a look at what we just discussed so far through the diagram. Okay, so we'll be looking at how spaces are allocated when table is created, and also how page status is changed. Okay, as you can see from the diagram, the memory table space has 8 pages, and they are all free pages. Okay, so let's try to create table called T1. Okay, so we executed create T1 statement. Okay, as the table T1 is created, the default free pages is allocated to T1, as the free page from the memory table space is occupied, which is changed from free to use, the white to red. Okay, so you wonder why memory table space allocates free page to the table, even though the insert statement is not executed. That is because whenever the table is created, the default free page is allocated by table space. However, there is no data inserted, so the page status from T1 is currently free. Okay, this is what I just talked about previously. The page status could be different when the page is in a table space or when a page is in a table. Okay, now let's try to insert on T1. Okay, now the insert has been executed on T1 as there was a free page in T1. Okay, if there was no free page in T1, then T1 would get free page from memory table space. Okay, so insert has been executed. The page from T1 is changed from free to use. Okay, let's try to insert another data into T1. Okay, so another insert has been executed on T1. Okay, now as you can see, there are not enough free pages in T1, so memory table space actually allocates free pages for T1. And because memory table space allocates free page to the table, so now the page status from memory table space is changed from free to use, and another free page is allocated to T1. Okay, just to let you know that memory table space allocates space in a unit of page, right? Okay, data is inserted, and page status from T1 is changed from free to use. Okay, let's insert another data into T1. Okay, another insert has been executed. Okay, same thing. The table T1 needs another free page. So as the memory table space allocates another free page to T1, the page 3, the page status of page 3 from memory table space is changed from free to use. And that free page is allocated to T1. Okay, now the data is inserted to T1. And the page status for page 3 from T1 is changed from free to use as well. Okay, so the key point is that when there are not enough free pages from the table, the memory table space actually allocates the free page for table in a page unit. Right? Okay, now let's have a look at how spaces are returned in memory table space. Okay, as you can see from the diagram, this memory table space consists of 8 pages, but all the pages are currently in used status. And table T1 and table T2 are allocated 4 pages each, So they are using 8 pages in total. Okay, so now let's try to insert some data into T2 table. Okay. Now the insert has been executed on T2, but we cannot insert some data in T2 as all the pages from memory table space are currently in used status. Okay, so now let's suppose that we cannot increase the max size of the memory table space, so there's no way we can get the free pages. But let's delete some data from T1 and see if the free page is returned to the table space, so that the memory table space allocates free page to T2 and inserting into T2 table would work. Okay, so let's delete some unneeded data from T1. Okay, so we execute delete statement on T1. Okay, as you can see, some data from T1 is deleted, the page 3 and 4, so their page status is changed from used to free, but the memory table space remains the same. Okay, the data is deleted, so let's try again for inserting data into T2. Okay, but still, we cannot insert data into T2. Why? That is because when delete statement is executed, the data is deleted, but free pages are not returned to the table space. And those free pages are only reusable within the table, right? Okay, so let's think of the other way. How about compaction? Let's try compaction this time. So we execute compaction in T1. Okay, as you can see from the diagram, the free pages from T1 are returning to the table space once compaction is executed. Okay, so now the free pages, page 3 and 4, are returned to the table space, and also page 3 and 4 from memory table space are also changed from used to free as well. Okay, so once page 3 and page 4 from memory table space are changed from used to free, they are ready to be reused by other tables. Okay, so let's try again to insert data into T2 and let's see whether it works or not. Okay, the insert has been executed on T2. Okay, as the insert has been executed, the memory table space can allocate the free page for table T2, the page number 3, and that free page from memory table space is changed from free to use. And also that free page is allocated T2 as well. Okay, once free page is allocated T2, the data is inserted and that free page is changed from used to free as well. So let's try another insert to T2. Okay, there's another insert statement to T2, so T2 needs another free page, so Tablespace allocates another free page, the page 4, by page unit. And same way, the page number 4 from memory table space is changed from free to use as well. Okay, once free page is allocated from memory table space, the data is inserted. So page status for page 4 from table is also changed from free to use as well. Okay, so we successfully inserted data into T2. So let's try truncate this time. So we're gonna truncate the table T1. Okay, so we just executed truncate on T1. Okay, after truncate has been executed, the data from T1 is deleted. Okay, after it is deleted, the page number 2 from T1 is now returning to the table space, but the page 1 is not returning to the table space. That is because even though the page 1 is a free page, the page 1 was the default free page when table T1 was created. Okay, so once page is returned to the memory table space, the page 2 from memory table space is changed from used to free. Okay, if you want to return page 1 to the table space as well, then you can drop the T1 table and page 1, the default free page will be returned to the table space. Okay, so we just looked at how spaces are returned in memory table space and how page status is changed in various situations.